I want to teach you, the difference between an endothermic and exothermic reaction. So endothermic reactions means energy has to be put into the system for the reaction to take place. Endo, into. Exothermic reactions release energy, so they get hot, so they're going to give off energy as the reaction goes. So there's two ways to illustrate an endothermic and an exothermic reaction. The best way, in my opinion, for you is to put it into the reaction. Do you notice this? Again, this is the reactant side of the equation, and this is the product side. Do you notice this? Now, nowadays we use kilojoules as our unit. Kilocalories is the older system that, we still see on our packages, that 100-calorie pack, etc. So that's the older system, but it's still a measurement of energy. So this is releasing energy. This is an exothermic reaction because it's over on the product side. Energy was a product of the reaction. So this is an exothermic reaction. Exothermic. So an endothermic reaction, I'm just going to make it up. So an endothermic, you would see your energy unit over here being put into the system. So if it goes into the system, it's an endothermic reaction. It means it's one of the reactants. And if it's leaving, it's an exothermic reaction. So this is an endothermic. That's a really bad looking in there. Thermic reaction here. So endothermic energy is on this side, exothermic's on this side. There is another way to illustrate that. So I'm going to always suggest that you put it into the equation because it's going to make your life so much easier. Okay, so we'll do a few of these and then we'll go to that little worksheet. Because when it's part of the reactants or products, it's going to be easier for you to see. But another way that it's illustrated is it's not written as part of the equation at all, but it's written over to the side. And we will actually learn something called enthalpy in this year, but you will see it as delta H, which means change in heat. And it will be, if it's an exo, it's going to have a negative in front. And so it's just going to be like written over to the side. So that's still an exothermic reaction. If it's an endothermic, then you would see a positive amount of energy. We'll just say 62 joules. Okay, not much energy in this one. And it would be a positive. So if it's positive, it's endo. If it's negative, it's exo. So the reason I say that is because I sometimes will give it to you this way. If I give it to you this way, not written in part of the equation, I would tell you to write it into the equation. So if it's exo, you're going to take this number and place it. That means energy is over on this side of the equation. Exothermic, losing energy. Okay, so energy is a product of that. If it is positive, then it is an endo. It's going to go into the system there. So the reason I say that is because a while ago when I said if you increase the reactant, if you increase this, which way is it going to go? It's going to go right. If you increase this, which way is it going to go? Right. If you increase this product, which way is it going to go? It's going to go left. So if you increase the energy, which is the product, it's going to go towards the reactant. So in an exothermic reaction, if you heat it up, that's how you increase energy. You would be increasing the energy, and it actually is going to be favoring the reactant side. Crazy. So exothermics, if you start heating them up, they're going to shift towards the reactant side. Endothermics, because they kind of like energy, if you heat them up, they're going to shift towards the product side, making more of that product. So if they're just part of the reaction, it's so much easier to see them as part of the reaction. Now the opposite of that is true. Remember when we decrease this, it goes towards the left. and I decrease this, it goes towards the left. If I decrease this, it goes towards the right. What if I decrease the energy? How in the heck do you decrease energy? You make it colder. You make it colder, you would be losing energy, and it's going to shift it towards the product side. On this one, if you decrease the energy, it's going to shift it towards the reactant side. And so that's how we're going to treat the temperature. So temperature does cause a problem. I'm going to pick on this one. I'm going to get rid of this here. I'm going to pick on this exothermic direction. I'm going to say, what's going to happen if I were to increase the temperature in this equation? Increase the temperature in this equation. Well, if I increase the energy, that's going to cause it to shift in that direction. Correct? Because if you increase this guy, it goes that way, increase. So what's going to happen here? Well, this guy's going to increase in value, this guy's going to increase in value, and this guy's going to decrease in value. And do you remember your constant? It is the products over the reactants raised to the coefficient power. I put reacts, but no reactants. Mark, get that fixed down there. Reactants. Now, so if the top is decreasing and the bottom is increasing significantly, guess what's going to happen to K? It's going to decrease. Decrease. So, what if I increase the temperature on this one? I increase the temperature on this one because it's an endothermic. Endothermic is, this is a reactant. We're going to see these guys go down and down and up, and you're going to see the increase on the top and a decrease on the bottom for your K. Can you see that you're going to see your K is going to increase? So the easiest thing for me to tell students is for temperature, because most students can figure out what's increasing, decreasing. For temperature, the K is going to mimic whatever your product is doing. Your K is going to mimic whatever your product is doing. Now, it bothers some students that why does temperature make a difference and the others don't? The others are just little mild disruptions and the system's able to get back to that same constant. But temperature is like a complete, you got to find a whole new way to live. A whole new constant, everything. The analogy I usually give is, what if my husband came home and says, hey, we're going to be moving to maybe Tyler, okay? Okay, well, Tyler's not much different from Texarkana. I'm going to probably have to adjust some, so it's going to disrupt my equilibrium, but I feel like I could get back to my equilibrium. But if my husband decided to come home and he said, hey, we're going to move to, like, I don't know, Alaska, where the temperature is a lot colder than it is in Texas, I have a feeling I'm going to have to find a whole new constant in my life, like a whole new wardrobe for one. So temperature disrupts the equilibrium so much that the constant doesn't stay the same. So it's the only thing that's going to affect the constant. All right, let's look at that little worksheet. Well, let's put that PowerPoint up there. So if heat is added to the system and the reaction is exothermic, heat should be thought of as a product, and the reaction shifts to the left, and the K is going to decrease. If heat is added to the system and it's endothermic, he should be thought of as a reactant, and it will shift to the right, and K is going to increase. So that's what I was just doing on the little sample there. So let's look at the page that we were working. Find it. Here we go. There's the Haber process. This is endothermic or exothermic. This one's actually written into the equation. This is an exothermic because it's on the product side. It's exiting the reaction. That's the way you can think of it. Exiting the reaction. So if I increase the temperature, so I'm basically going to increase a product over here. If I increase a product, I'm going to shift to the left. And these two reactants, this is N2 and H2, they're going to increase. And what's going to happen to your product? It's going to decrease. This was your constant. Your constant is going to do whatever your product is doing. What the heck is your product doing? This was your product, and it is decreasing. Because temperature is the only thing that affects the constant. Constant can't stay constant at a different temperature. If I decrease the temperature, it's like reducing a product. If I reduce the product, I've got to make more product, so it's going to go to the right. You're going to see your two reactants go down. Your product is going to increase, and what's going to happen to your constant? It's going to also increase. It does whatever your product does. That's the easiest way to learn how to do that one. All right, is LeChatelier's. Oh, let me do one more thing. So a catalyst, we talked about a catalyst speeding up a reaction, right? So a catalyst will make a reaction go faster, but it doesn't disrupt the equilibrium. So it doesn't cause a shift. We just kind of get to that balance faster. We get there and then we stay balanced. So catalyst, if you say a catalyst, the answer is no effect. Just like a solid reactant or product has no effect on the equilibrium. So catalyst also has no effect. Also an inert gas, I think I took those questions off, but inert means it doesn't react, so that wouldn't cause an effect either. All right, that is LeChatelier's shift. So please ask questions if you need help.